Good morning, everyone, or afternoon, or evening, depending on what time of the day or night it happens to be for you. And welcome back to the channel. More specifically, welcome back to the IP subnetting mini-series. And this will be part 2 of that series. So in this video, we're going to cover IP subnetting based on a network requirement. So if you need a specific number of networks, that is what we're going to be covering today. First of all, I'm going to do a quick recap of what we learned in part 1, so subnetting based on host requirements. And I'm not going to go slow, so if you haven't watched part 1, I advise that you stop this video, go back and watch part 1. It should be linked in the description below. So let's start with that recap, and then we'll move on to subnetting based on a network requirement. So to recap, we're going to use the same Class C network as we did last time. So 192.168.1.0/24. And off the top of my head, let's just say we need at least 40 hosts, wasting as few IP addresses as possible. Of course, you should already know by now what the subnet mask will be, since we see the /24 CIDR notation, but let me just write it out anyway. So we have 255, 255, 255, 0. Okay, so 40 hosts in each network. We'll start by making our chart at the top of the screen. So 128, whoops, so I hit the eraser. 128, 64, 32, 16, 8, 4, 2, 1. Okay, so step 1. Convert to binary. So we want to take this 40 right here and convert it over to binary. So we see 128 is too big, 64 is too big, 32 will fit, and then we really don't need to worry about anything else, because at this point we know that it is going to take 1, 2, 3, 4, 5, 6. It's going to take 6 bits for the host to size this network up appropriately. So if we convert our subnet mask into binary, so step 2 will be convert mask to binary. The subnet mask right here will be 8 ones, so 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Then we have our 6 host bits that we need to reserve. So that means we would need to pad that with, since host bits, remember host bits are on the right, we would need to pad that with 2 network bits to make sure we have the appropriate amount of host bits. So we will go 1, 1, and then 1, 2, 3, 4, 5, 6. Okay, and then this subnet mask right here will now be a, in CIDR notation, a slash. So we have 8, 8, 8, then 2 over here. So 8, 16, 24, 26. So we'll now have a /26. So our first network will be 192.168.1.0/26. The new subnet mask of 255, 255, 255. And we look at these right here. Go up to the chart. 128 plus 64 is going to be 192. Okay, and then the last step is how do we figure out exactly how many hosts we will be able to contain in this network, since like I mentioned in part one, most of the time you're not going to be able to achieve the exact number unless it falls on a specific spot. So if we were to look at the number of host bits, which is 6, and we did 2 to the power of host bits, so 2 to the 6th power equals 64, and then minus 2 for the network ID and broadcast, end up with 62. So even though we were going after 40, this network will be able to contain 62 hosts. Now, if you remember back in part one, if we did less, so if we tried to conserve even more, so say we did 2 to the 5th, so we only had 5 host bits, then we would have 32 minus 2, and that would only be 30. So anyways, yes, we'll have 64 total IP addresses in this network, 62 usable hosts, and then to find the number of total networks of 62 hosts, simply just go 2 and then to the power of network bits, so 2 squared, and that will equal 4. So we'll have 4 networks of, say, 64 addresses, and then 62 usable. And again, I apologize for my messy writing. It's going to take me a lot of time to get used to this pen and writing on a screen versus a piece of paper. So, okay, and then last step in our recap is just finding the increment. So we'll find where this network ends and then where the next one begins. So again, we look at this new subnet mask converted to binary. We look at the 4th octet, since it's a class C. We see these 2 right here. Again, go back up to our chart, and we see, so 1, 1. So we look at the 64, so our increment is 64. So that means first network is .0, .64, .128, etc. And then fill in the rest. So 0 through 63, 64 through 127. And then, of course, this would be network ID, this would be broadcast. So usable would be .1 through 62, .65 through 126, so on and so forth. Okay, that was the recap. Actually, let me just back out here and open up a new whiteboard. Okay, so next we're going to subnet based on a network requirement. So we're going to use the same class C address, 192.168.1.0/24. Stick in the subnet mask. And that is supposed to be a 5. And let's say we need, just pulling this off the top of my head. Let's say that we need, 32 networks. We're not really concerned about hosts. I mean, this is purely example, so I don't really know of a time when in an IT department you would just randomly choose the fact that you need 32 networks. But obviously, for an example, we're just going to go with whatever it is that I think up at the moment. So I'll just say 32 networks. Okay, now this should be fairly easy and fairly quick if you understood what we just recapped a moment ago, because it's going to be the same thing. It's just going to be the bits that we're going to change are going to be different. So subnetting based on a host requirement, we pad it with the ones, so that way we can accommodate the exact number of host bits we need. But when we're dealing with networks, we're going to actually be looking at the on bits, so the leftmost bits that will be ones. So, but everything else will be the same. So we'll start with our chart. Okay, convert this guy to binary. You know that 128, nope, 64, nope, and here we go. 32, this actually falls exact, but it's still going to take us 1, 2, 3, 4, 5, 6. It's still going to take us 6 bits on the network side to divide this Class C up into 32 different networks. So once again, we will convert the subnet mask into binary. Oop, not 1.1.1.1. Go 8 ones, so 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And then this is where the 6 network bits come into play, and we need 6 of them. So just like before with the host bits, say we needed 6 host bits, like I believe we just did in the last example, we would put 2 of these so we had room to accommodate those 6 host bits. But now since we're dealing with the number of networks, we need 6 network bits, so 6 on bits. So 1, 2, 3, 4, 5, 6, and then 0, 0. Okay. So now we know we have 8 here, 8 here, 8 here, and then 6 over here. So 8 plus 8 plus 8 is 24, plus 6 will give us 30. So we know our first network here is 192.168.1.0/30. The subnet mask of 255, 255, 255. I want to say off the top of my head it is 252. Just use a calculator just to be sure. So we'll go 128 plus 64 plus 32 plus 16 plus 8 plus 4 is 252. Okay. And then to figure out the number of hosts is the same. So we want to look at the host bits over here. 2 squared equals 4. Minus 2 would be 2 usable. Now this actually works out perfectly, because some of you might be thinking, well, what, and again, we realize that this is just an example, but 2 addresses is perfect in the real world, because that's exactly what you would need for a point-to-point link. So this would work out very well if that is what you were breaking down this Class C. If you were breaking it down to make multiple little networks for point-to-point links, this would be perfect. And then, of course, figuring out the exact number of networks, go 2 to the 6th. And that would be, I'll use my calculator for this as well, that would be 64. And just check one thing really quick. So here's the thing. Now, I don't want to throw anybody off, because I know I've been doubling down on this in the beginning of this video and the last video about going one less. There is a certain rule. I would have to look it up to figure out the way it's stated verbatim. But there's a rule that basically states if it falls on a certain number, and in this instance 32, you can actually deduct 1. So here we were looking for 32 networks. We ended up with 64. Typically, the way this works is that this is what you would be looking at, and if you deducted one more bit, you would end up with less than what you needed, so less than 32. In this situation, it just so works out that if we were to only use 5 bits, we actually get 32 on the dot. So we actually, in this example, and you'll see this happen occasionally, and when it does, if that is exactly what you need, then you can go with that. So we could go with just 5 at this point. And with that being said, that will actually change everything. It'll change the subnet mask, so we will have 1, 2, 3, 4, 5, and then 6, 7, 8, which will change this from a /30 to a /29. And it will also change our subnet mask from a 252 to a 248. I'll have to look that rule up and see if I can post it in the description, because it'll basically tell you whether you're doing networks or hosts, which increments will allow you to do that. Or, like I said, you can just go ahead and just do, like in this example, we were at 2 to the 6 because we thought we needed 6 bits. Do 1 down, and hey, if it comes out, then you know that you're good, and you can deduct 1 more bit. Okay, so let's just recalculate our new network. So now we'll go 2 to the 3rd to figure out how many hosts we'll have. And I want to say that'll be 8. So 8 minus 2 for the network ID in the broadcast. So that'll give us 6 usable hosts. Now, this might be a great network size for, and I know we're using an RFC 1918 address here, but say you were an ISP and you were using public IPs, a /29 would be great to allocate to your customers if they needed some static IPs, if they needed more than just one, or if you had a network segment that you were running first hop redundancy protocol on. So say like HSRP. So you have this would /29 would give you the perfect amount of addresses you would need, because you would need an IP address for each interface for each device on each side. So say you had 2 routers, and then I'll just put a switch right there, and 2 routers right here. And this was .1, .2, .3, .4. And then we had the virtual IP for HSRP. And say that was, virtual IP was .5, and down here was .6. That would be perfect. A /29 would be perfect for a scenario like that as well. Okay, so 6 usable addresses, and we already know the number of networks because we just figured that out. So 2 to the 5th is 32. The only thing left to do is find our increment. We look at these. We know that there's 5 of them. Go up here to our chart, which is getting kind of messy at this point, but so we have 1, 2, 3, 4, 5. Increment is 8. So the first network will be .0, next will be .8, .16, .24, so on and so forth. So 192.168.1.0, 192.168.1.8, 192.168.1.16, so 0 through 7, 8 through 15, 16 through 23. And then, of course, usable for our 6 usable addresses. The 0 is the network ID, so this would actually be 1 through, and then the 7 would be the broadcast, so 1 through 6. Down here would be 9 through 14. And, sorry, I was losing my train of thought for a second. 17 through 22. And my battery is ready to die, so I'm going to have to wrap this video up. Yeah, that's pretty much it. I hope you learned something in this video. Stay tuned for part 3, where we reverse engineer a subnet mask. So, say you have a network that is a say a /18 or something like that, and you see that on a router or a PC, and you're like, what network does this belong to? I'm going to show you how to reverse engineer the subnet mask, find the network boundaries. And then I think I might also add a part 4 as well, where we go over a couple different subnetting examples, and I will kind of do them for you so you can follow along and hopefully get the concept ingrained in your mind a little bit better. So anyways, thank you so much for watching this video. I hope you learned something, and I will see you in the next one.